Hola a todos, soy Julián de Sistemas de Francia y voy a hacer la clase en inglés porque en español no es muy bueno. So yes, I switch into English. I'm also part of the CROCO developers. So you can find my contact on the CROCO website if you need. And today we're going to start the morning talking about coupling with OASIS. So first I will give you for maybe 15-30 minutes some introduction about the coupling philosophy with OASIS. And then I will move to practice. So we will try to make a couple of simulations. So for this morning, we will be doing this simulation, let's say, by hand. So by trying to modify all the files that are requested. And tomorrow morning, we will use some other specific scripts and toolbox that we developed for easier to run. So when you have to run multiple years or multiple months in couple mode, it's helping you dealing with the dates and moving up the file, preparing the files. But today we will go simpler and just start understanding how the coupling is working. Okay, so let's start. I will put my screen for a moment. Okay, so coupling with OASIS. So basically, what we want to do is couple several models like ocean and waves for today, but eventually with atmosphere too. And we can do that in multiple ways. In the community, there are several couplers that exist. You can have some embedded models, so you have only one executable, but the idea with the OASIS coupler, it's a library. And it's just helping the models communicate together and exchange some variables, but you have still executable for each model. So basically, it's a representation that I've done there, putting the OASIS library in the middle, so it's helping the models communicate and interpolating data between waves. So this coupler is developed in France, in Fairfax, in Toulouse. And as I said, it is a set of libraries, so it's not an executable file, it's libraries, and it provides several functions which are called in the models themselves. So these different functions are functions to exchange variables, to perform eventually time interpolations of these variables, so for example, averaging over the coupling period. It also performs parallel exchanges for performance. And it performs grid interpolations because you can run a couple simulation with a different grid for each model. You can also use the same grid, but eventually, if you don't have the same grid or the same resolution, you have to perform grid interpolations. And this is performed by the Spreaker library. This coupler has several advantages, in my opinion. So first, it's non-intrusive. So you have only a few calls to the library in the model. You will see I have put some schematics after to show you how it is implemented in the code. So it's an easy implementation of this library. And it's a common interface for a variety of different models. So if you interface your code with OASIS, then you can communicate with any code that is interfaced through OASIS. So basically, we have OASIS in CROCO, but there is also OASIS in NEMO, which is another ocean model. There is OASIS in SOFX, which is a model that is connected to the atmospheric models from France weather forecast and also IPSL, so climate models. We have OASIS in WaveWatch. We have OASIS in various atmospheric models, also in WARP, for example. So basically, the way OASIS works, as I said, it's called in each model. So this is a representation of that. So in each model, we will call different OASIS functions. The first is initialization, because OASIS is managing the communication between the model. And to do that, it needs to initialize the communicator. And for that, it's using the MPI communicator. So it's something important. You will use MPI to make OASIS work with your models. This is something quite important. Then you have to call some function for the definition of the grid and of the variables to be exchanged. And finally, you enter the temporal loop of each model, and there you have some function to put and get some variables, so to send and receive variables from one model to OASIS memory, and OASIS memory will provide this variable to the other model. And finally, there are some functions to end the copying, so terminate stuff and close the communication between the models at the end of the run. So I won't go into all the details of this. It's how it is implemented in CROCO. So if you know well the CROCO code, it's just to show schematically where the functions are called. So we have only 6 additional routines that are for the coupler, that are all named CPL prism something, because the former name of OASIS was prism. And so we have a routine for initialization, a routine for definition, a routine for the grids, and a few routines to get and put variables, to send and receive variables. And into these CROCO routines, we have the calls to the OASIS library. And it is the same in the WaveWatch 3 model. So in the different WaveWatch 3 routines, there are several new modules related to OASIS that are named CPL OASIS something. And there you can call the different OASIS functions to communicate with the other model. So this is if you want to really get into the code, but it won't be necessary to understand all that today. Then the idea of the coupling, we have the coupling sequence, is that we have one model with its own start files and its own time stepping, and we have the other model with another initial restart file and eventually different time step. Okay. And in the middle, the OASIS will store the variables at each time step of the models and eventually keep them to compute some averaging, for example, in time. And when we decide to exchange variables, so this is the coupling frequency, OASIS will exchange variables between the models. Okay, so this is the idea. And then it's going for the next time step, etc. OASIS also requires some restart files to start the simulation, because as you can see, both models will start at the same time. So this is very good for performance. So the models run exactly at the same time. They don't have to wait for each other. But then we need to have variables at the beginning. So OASIS needs to give some variables to the other models. So we need restart files. And we will see that we have to prepare these files in advance. And at the end of the simulation, OASIS will write into this restart file again if we want for use them eventually in the next run for a restart for the next run. So all these settings are performed. We don't have to set everything within the model. As I said, it's very non-intrusive. And we will decide what variables to exchange at what time step with what type of time or grid transformation through a file that is named the namcover. So it's a kind of named file for OASIS that will help you set up all the information that OASIS will need to exchange variables between the models. So basically, it's a text file, simple text file. And I put here some sections of this text file. So in this text file, there are some keywords and then numbers explaining what the keywords are doing. So you will specify the number of things that you will exchange. Then you will specify the number of models that OASIS have to deal with and the name of the executable of these models. So you can see it's not the usual name of the models. So for WaveWatch, generally it's WW3 shell, but here we have renamed it WaveWatch. And for CROCO, it's CROCO-X here because it was mandatory to have 6 characters for the name of the models. So you just change the name. And then you have to specify the time that you want to perform for the simulation, because as I said, OASIS will initialize the time and then terminate the simulation. So it needs to know when to terminate the simulation. Then you have some keywords and some numbers for debug information. So here it's put to 1, it means not so much debug. If you want more information about OASIS, you need to increase this number. And you will see that sometimes our OASIS errors are not very easy to understand at the beginning because you have a lot of logs and stuff like that. But if you need more information from the coupler, you need to increase these numbers. Then you will have a section for the variables. So here I just put one variable example. So you have to specify for each variable if you want to exchange between the models a few information. So here, for example, we want to exchange the sea surface zonal current. Okay. And you can see that we need to have specific names for these currents for OASIS. So there are names that are coded in the specific routine that are in each model for OASIS with a specific name. So for example, in CROCO, this variable is named CROCO2023 for eastward ocean currents. And in WaveWatch, the OASIS name of this variable is named WaveWatch3 or SS3. This is like this, you cannot change that. So there is a table that can help you to understand and know what the variable names are. And also, you will see that in this NumCouple file that we have, there are comments and all the variables are in there. So if you're a bit lost, you can just refer to the comments and you will see that. So here we want to send CROCO ocean surface velocity towards WaveWatch. Then we have to specify in red here what is the coupling frequency for how many seconds do we want to exchange this information. So here, for example, it's 1 hour. Then we have a number that specifies the number of transformations we want to do to this field. So here we will do 2 transformations. First, we will do an average in time, because maybe the time step of CROCO model is less than an hour, and we want to average 1 hour before giving the surface velocity to WaveWatch. And we also have a grid transformation to interpolate the variables towards WaveWatch grid. So there are 2 transformations, and these 2 transformations that are specified in these last lines with some keywords. LogTrans is saying time transformation, script_r is saying space grid transformation, and then we have 1 line per transformation. So 1 line is for time, so average here, and the last line is giving information on the type of grid interpolation. So here there are specific keywords. They can be found in the OASIS documentation to understand what they mean. But basically here it's distributed weight type of interpolation, and it says it's on a lateral grid, stuff like that. Then here we have in pink the name of the restart file for OASIS, where OASIS will find the first ocean velocity and where it puts the ocean velocity at the end of the run for the next run. And then we have a last keyword that say, okay, you will write this field just at the end of the simulation. If you want that OASIS write this variable at each time step taken, it's useful for debug, but for running, you should not do that because it will take much longer to run because it has to write things all the time in an XBF file. Then you have a line that specifies the size of the grid. So first you have the size of the CROCO grid, then you have the size of the WaveWatch3 grid. Here they are the same, but they can be different. And then you have the name of the grid that is for the coupler. You will see there are some specific NetCDF files that are generated by the code for OASIS to know the grid and to prepare the that was 1 hour, so we put 1 hour there. It's in seconds, obviously. And this is just to help the coupler understand when is the last time that it will take variables from the model before, for example, averaging and exchanging with the other model. And finally, the third line is giving us some information about the grid. So it's say it's a regional grid, because we could have a global grid or something different. So the two first are for the CROCO grid, and the two second are for the WaveWatch 3 grid. And 0 is the number of eventually overlapping points. So for example, if you have a tropical channel all around the Earth, you can say to OASIS, okay, I have some overlapping points. So the grid information is properly set up if you have like a tropical channel and you want the two borders to communicate together. So you can put periodic condition and a number of overlapping points. But the most usual case is R0, R0, because you have a regional area. Then here I just put the different variables that we can exchange between CROCO and then WaveWatch 3. So first, the CROCO field that can be sent and received. So in CROCO, we can send the SST. This is for the atmospheric coupling. It's not useful for the waves. Then you can exchange the ocean surface velocity in the U and V direction. So this is in the X and Y direction of the grid, but you can also exchange the eastward or northward. Sometimes it's the same if your grid is just oriented eastward and northward, but if you have a rotated grid, it won't be the same. And it's quite important because, for example, WaveWatch is supposed to receive eastward and northward ocean surface current. So you need to exchange eastward and northward if you have a rotated grid, and not human being. Then you can exchange the sea surface elevation, which is useful as the waves. And what are the fields that CROCO can receive? It's typically significant wave height, mean wave period, mean wave direction, wave to ocean kinetic energy flux, mean wavelength, bearing head pressure, wave orbital bottom velocity, surge drifts, component of the stress that is given from the wave to the ocean, in the X and Y direction or in the eastward and northward components as before, and part of the stress that is given from the atmosphere to the waves. I will come back to these specific things a bit further in the afternoon, because we have some specific about this stress prescription from the waves to the ocean or from the atmosphere to the ocean. But basically, we have all these variables that can come from the wave models. But today, we will only take the HS, so significant wave height, mean wave period, and mean wave direction. And the other variables will be approximated from these three variables. This is something that is possible also in the code. So we have like typical linear and parametrization to compute, for example, the stop stream from these three mean bulk wave variables. Then the field that WaveWatch can send are basically the same. So what, because we need to say WaveWatch, okay, send me the significant wave height, for example. So, but you see that they have different names. And in WaveWatch, all these names, like in CROCO actually, are 8 characters because it was mandatory in the previous version of OASIS and it stayed this way. Now you can have longer names, but we still have these 8 character names. So be careful. For example, for the significant wave height, there are 2 underscores to put so it's something to remember. Sometimes it can give you some trouble. And the field that WaveWatch can receive then is the eastward and northward ocean surface velocity and the sea surface elevation. So what OASIS then can do is time transformation, as I said. So here I put the typical time transformation that we can do, but basically in general what we use is average, because we want to have average values. Eventually to couple high frequency, you can use instantaneous field exchange, so no time transformation, but basically what we use the most is average. And then there are different spatial interpolation between the grids. So here, for your own area, I suggest that you try some of these, because if you are in the coastal zone, for example, it can be quite different between the parts that are massed in the coastline and the ocean. So I just advise you to try a little on the configuration that you know well to see how the fields are transformed by the different kind of grid manipulation. And as I said before, so all what I told is managed here by the NAM couple, as I said, but we also need some restart files for the coupler, specific for the coupler. And these restart files, we have to build them before starting the run. So here is a summary of what we have within OASIS. So we need restart files, we need a nameless file, which is named the NAM couple. And what OASIS will generate is typically it will generate some grid-related files. So it will generate a grids.nc file, a masks.nc file, and an areas.nc file. It's just all information about the grids of the two models, because it's useful for OASIS to make interpolation. Then it will generate also weight for interpolation. So you have an HCDF file that is explaining what are the weights between one grid and the other. So you will have two files, one that is from the wave-water grid to the ocean grid, and the other that is from the ocean grid to the wave-water grid. Okay. And finally, you have several log files that you need to remember because you will use them in case of error. So there is a general OASIS log file. Then there are specific files for each of the models. So the timers are just log file and time statistics. But the one that you will use the most is a debug routes with a number. So the first one is for the first executable, and the second one is for the second executable. And generally, here is where you find your error, if you have. And there are also the not routes. It's for other processors, because you know when you run into MPI, you have one master MPI processor that is generally managing the information, but eventually sometimes the error can arise somewhere else and not send this information to the master processor, and so then it's written in the not root debug file. So just to give you a summary of the steps, what you have to do when you want to set up a couple simulation. So if you have only one model, the usual that you do, for one model you need input files, so grid, initial condition, boundary conditions, and forcing, for example, surface forcing. You need to have your model executable, and you need to have your model named. This is for one model. Now you have two models, so you need the same for the other model, okay? And in the middle of that, now you have OASIS. And for OASIS, you also need input files, so typically the restart files, and you need also names. So you can see that it's a lot of files to manage. This really is the difficulty today. And all this will bring you log and outputs for each of these components. So you will have your usual logs and outputs from your CROCO models. You will have your usual logs and outputs from the wave-water model, and you will have logs and outputs from the OASIS coupler. This is it. So I think we can. I can just introduce the practice, and then we can have a break if you want, or we can keep going a little.
Okay.
So basically, what we are going to do this morning as a practice, and this is a summary of the different steps that you need to do if you want to build your own area to run a couple simulation. So first, obviously, you need to get the source codes of the different models and of the OASIS coupler. Then you have to set up your architecture and environment with the machine you will be running. Then you have to compile the code. So first, it's very important, as OASIS is a library that will be used in the different models, you need to compile it first. So first, you need to compile the OASIS coupler. I've done it for you today, but I have also the explanation to do it by yourself if you need. And then you have to compile your code with the same library, so same Next.js libraries and same compilers. It's very important, otherwise it won't work. And you have to make a link to the OASIS library during this compilation, so that the codes can know where to find the library and to use the function of OASIS. Once you have all your code compiled, you can pre-process your different models, so prepare the grid, the initial condition, the boundary condition, the surface forcing. Then you have to prepare the name list for each model and for OASIS, and the input files for OASIS. And finally, you can run the simulation. And this run is done by launching all models together, and they will communicate through OASIS. And then in the end, you have some outputs that you can check and look at your results. Here, I've written that the steps 5, 6, let's say, can be alternatively done using a coupling toolbox. Because as I showed a bit earlier, you see that you have a lot of things to fill in the non-couple, like the grid size, the time steps, the dates, the time of the simulation. And this you have to be consistent between OASIS and the different models. And it generally generates a lot of errors, because if you just do one mistake, it won't work. So we have built a toolbox of script that helps you do that. So it's just filling automatically a lot of files and moving those files to the directory you want to run, and then moving the outputs to another directory. And it's managing the date. So for example, if you want to do a 1-year simulation with that is split into monthly simulation, and you want to restart each month your simulation, you can just say that with a script, and it will perform all the change in the date for each month automatically. So it's useful, but as it's not, it's a bit like a black box when you start using it. Today we won't use it, and we will change everything by hand so that you understand how the coupling is working, and tomorrow we will try with the toolbox. So basically this morning, what we will do is the Benguela classical configuration of CROCO. So as we said a few days ago, it's an historical configuration that is on the Benguela upwelling region. And it's very useful because it's at relatively low resolution. It's 100 degrees, so it's not a big number of points, so it's running fast. So for tutorial, it's very useful. And I advise you, when you want to start doing coupling, even on your own computer, start with this area so that you can see that everything is working well, so you won't have any issues with the code, the compilation, and stuff like that. And then you move towards your own simulation. It's because this one, everything is almost set up automatically from all the files from CROCO and from the copying tools. And so if you manage to make this work, it will be much easier for you than to make another area work. So I've put here, so you can refer to that a bit later, because you have this PDF in the MOSA usual repository online that you can download. So if you need, you can come back to this slide where you have the main information for the grid that we will use and the time steps for each model that we will use today. So we use the classical grid that is defined there. So note that here you have the number of points of the grid, which will be important for to fill the non-couple. You also have the time steps of the CROCO model. So the baroclinic time step will be 1 hour, and the barotropic will be 60 seconds. For the wave-watch tree, we will use the same grid as CROCO today. Because as Andres said yesterday, we have a little script that can help you make the exact same grid from wave-watch for wave-watch and CROCO grid, just making things easier. But you can have a different grid also. My advice also regarding grids, when you do coupling, is that you should have grid data quite consistent within each other. So either that can be the same. If you want almost the same resolution, I really strongly advise you to have the same grid. Because, for example, if you work on in a coastal area, if you don't have the same grid, you won't have the same land points in different models, and OASIS will manage that, but in a physical consistency way, maybe it will be a bit difficult. So if you have bays that are seen, for example, by the wave model, but not the ocean model, or the opposite, it can bring you some strange things. If you want a different resolution that you can have, for example, you want higher resolution in the ocean than in the wave model, you can do that also, but I advise you to have a number of grid points that fall within the larger grid. Generally, it brings you more consistency. And also, on the extent of the grid, you can have two grids that don't have the same extent, but and OASIS will manage that. But what OASIS will do, if you don't have information outside of the grid, because you have one little grid communicating with a larger grid, in the larger grid, it will just extrapolate values of the inner grid. So be careful with that. There are also ways to prescribe some data out of the domain where you don't have data. But generally, I would also advise to have quite the same extent grid to avoid issues. So here are the time steps for the WaveWatch 3 simulation. You remember from yesterday, in WaveWatch there are 4 different time steps. Okay. And so generally you start to compute the CFL time step, which is the constraint of the numerics in the model. And this is generally 4% of the delta X, 3 or 4%. Then you compute the global time step, which can be 2 to 3 times this time step. Here it's 3 times. And then you compute the refraction time step, that is generally half of the global time step. And for the source terms, you have here 10 seconds. Andres said yesterday that it was between 5 and 60 seconds. It depends on the frequency of your forcing and on the process that you want to model. You can keep it to 10 seconds most of the time. And for the coupling frequency, today we will couple the 2 models that are running both with a 1 hour time step every 6 hours. Okay, and we will perform an average of every 6 hours of the variables that we want to exchange. And we will run for 30 days, starting in January 2005. And we will run, this is another thing important, with MPI, because it's mandatory for OASIS, with 2 CPU for CROCO and 2 CPU for WaveWatch. So these are the basic settings. I think we can go for a quick break before we start things.
Okay, we'll stop.